Hello and welcome to section 4.4, the fundamental theorem of calculus. And in this one, this is the section that everybody's kind of been waiting for because the summations have probably at this point been quite cumbersome. And so we're getting kind of tired of them. But somebody along the way realized that there was a pattern that was happening. And some of you guys may have discovered this pattern when you're doing these problems, but there is a link between the definite integral, which is what Riemann was talking about, and summations. And so instead of going through and doing all the summations every time, they realized that if you take the antiderivative of the function that we're dealing with and get a new function and plug in the upper value and subtract away the lower value, you will end up with the area under the curve, and a fairly accurate one. And so that's what this is all talking about here. And we have these functions. I have a couple examples down here you can kind of look at, and I'll do a couple examples on the next page. But here's basically our things, is that you need to be able to evaluate the definite integral without having the use of limits of a sum. Well, that's what we want to do. And so we'll apply the fundamental theorem of calculus, and that's where we do the upper minus the lower plugged in. And then you don't need to add on the constant of integration to this, because you're adding on a constant and then you're subtracting that exact same constant, so you don't need to even bother with it. So let's practice this real quick. So instead of going through the whole summation thing, which is what we could do, and having an infinite number of rectangles between 1 and 2, we're actually going to go, oh, we'll take the antiderivative of this, which will give me x cubed over 3 minus 3x. And if I plug in 1 for x and 2 for x, so if I was to plug in 2 for my upper limit, I would get 8/3 minus 6. That's my upper, plugging in my 2. And then I'm going to subtract away my lower, which is 1/3 minus 3. And so then just simplifying that, well, 8/3 minus 1/3 is 7/3. And 6, this is minus a negative, so it's negative 6 plus 3, which would be minus 3. So it looks like I'm left with 7/3 minus 9/3, which gives me a negative 2/3 for area. Now you're probably asking yourself, how am I dealing with 2/3 for area? Negative 2/3, well, that's an area below the x-axis. And so then the next example, we're going the 3 times the square root of x, which I'm going to write like this from 1 to 4, 3 times x to the negative 1/2 dx, or to the positive 1/2, sorry. And so then if I was to raise that up a power, it gets 3/2. So my new term, when I do my antiderivative, will be x to the 3/2 times 3 divided by 3/2. And I'm going to take that from 1 to 4. And so then this 3/2 would get flipped over, so the 3's will cancel out. So my new function is 2x to the 3/2 from 1 to 4. And so now, plugging in what I know, it's going to become 2 times 4 to the 3/2 minus 2 times 1 to the 3/2. Now remember, if you don't remember anything about fractional exponents, you can do these in any order you like. I could cube 4 and then take the square root of that answer, or it might be more advisable to take the square root of 4 and then cube that answer. And that's the way I'm going to go about it. I'm going to take the square root of 4, which is 2, cube it, which gives me 8. So 2 times 8, and then over here I end up with minus 2. So my total area is 16 take away 2, which is 14. And then finally, over here we have a trig function, and when we do we took the derivative to get secant squared, so that meant that this becomes tangent of x when I do my antiderivative from 0 to pi over 4, because I differentiate tangent to become secant squared, so I'm going backwards. So I just have to ask myself, how did I get secant squared? Well, took derivative of tangent. So now plugging in those values, it's going to be tangent of pi over 4 minus tangent of 0. Well, tangent of pi over 4 is 1, minus tangent of 0, which is 0, so the area under that curve is 1. So then how does this apply? How can we do this if we have a function? Well, we can do the same things that we end up with. In this example, we're going to find the area of this under this curve using this function. So we would do our definite integral from 0 to 2. That's my lower limit and my upper limit. And then my function is 2x squared minus 3x plus 2. And don't be lazy about this dx, because remember we were talking about the delta x before being a width of the rectangle. And so this dx is the width of the rectangles, and if we make that go to infinity, that's where we get our, this is our height, the function is our height, and the delta x is our width. So we can't be lazy about that. We got to kind of keep track that we are still finding area of little rectangles. So now if I do my antiderivative of this, I get 2x cubed over 3 minus 3x squared over 2 plus 2x, and now I'm going to go from 0 to 2. And it's just a matter of now plugging these guys in and subtracting them. 0 is always our golden child in these, because if you notice, if I put 0 in, I'm going to end up with nothing over here. So I'm going to have 2 cubed to the 2 times 2 to cubed over 3 minus 3 times 2 squared over 2 plus 2 times 2. Alright, so now it's just a matter of simplifying this, and I get 16 thirds minus, here we get, it looks like 12 halves, and over here we get plus 4. So 12 halves is negative 6, so we really have 16 thirds minus 2, and then if we get a common denominator, it'd be 16 thirds minus 6 thirds, which is 10 thirds for my area under that curve. And that's really all we're trying to do. And you could do a summation and you'd find the same thing, but I'm guessing that at this point you probably don't want to have to do a summation anymore. So then we have the average value of a function, and the average value of a function is basically just giving me a rectangle that will kind of average the area. So you'll notice we have a little area above the curve and this area below the rectangle. So we have this area that's extra, that's the light blue, but then we have this pink area that's above, and so we're just trying to find a rectangle that will average this. And so you'll notice that the only thing really new is this 1 over b minus a, which is our lower limits, which will give us kind of an average rectangle for this. And so how would this work? Well, we could find this rectangle here. We don't know exactly where the height is, but we could find that the average area of this rectangle that would kind of average this curve. So I'm going to say 1 over b minus a from a to b of f of x dx is what we're dealing with. Well, b is 4, a is 1, so 1 over 4 minus 1 from 1 to 4 of 3x squared minus 2x dx is what we're dealing with. So we get 1/3, and so then if I do my antiderivative of this, 1/3 times x cubed, because we multiplied by 3 and divided by 3, minus x squared, because we multiplied by 2 and divided by 2, and we're going from 1 to 4. Well, then that means that I get 1/3 of, well, plugging in 4, I get 4 cubed minus 4 squared, and then over here, I guess I'll just leave the 1/3 out and subtract 1 minus 1, and so that's really becomes 0 over here. And so we really have 64 minus 16, which is 1/3 of 48, which would give me 16 for that area of that average rectangle. Well, how does that work compared to the actual value? Well, it's an average of it, so you're going to get 1/3 of what's going on there. So then what you got to understand about our definite integral is that it is kind of an accumulation process. And so what we're trying to do is, it just depends on where we're going to find the values. If we go from 0 to 0, then we'd have no area, and so it looks like this. If we go from 0 to pi over 6, we're gaining a little area, and each time we're be gaining a little bit more area as we go across. So what I'm trying to get at here is that on the AP test, they're going to say how much sand is accumulating or something to that effect, and that would be found by doing the definite integral. And so then we have a second fundamental theorem of calculus, which basically says that the antiderivative and the derivative are opposites of one another. So if I take the derivative and try to take the antiderivative of something, I'll get the function back. And so that's really what we need for our second fundamental theorem of calculus. This is how calculus works, is that we plug in a function, we get our value back. And so you can see if I take the derivative of this, the only thing that changes is the t goes to an x. You might be asking, where does the 0 go? Well, remember that if I was to do this, let's do this slowly here. If I take the derivative and then the antiderivative of this, it would look something like this. And so the antiderivative of this function, using my definite integrals, would be negative sine of x, right? And, well, no, wait, I differentiated sine to get to cosine, so it's not negative. So it would be sine of x, plugging in the x, and then minus sine of 0. Well, sine of 0 is 0, which it could be any number, but if it's 0 in this case, now if I take the derivative of that, well, the derivative of sine is cosine of x, and the derivative of a number is just nothing, so that's how we get back to this. So that's the second fundamental theorem of calculus, saying you can do the derivative and the antiderivative. Well, here's another example of this, and basically the second fundamental theorem of calculus is trying to give us a shortcut, and we'll do more examples of this with different values at the top up here of this, but the short and sweet answer for this one is you'd get x squared plus 1 underneath the square root. And that's really what you get for when you take the derivative of the antiderivative, is you just plug in that number. And we'll talk more about this in class. So if you have any questions, please come to class prepared to ask them, and we'll talk more.